Hi, this is Knowledge Quest 3 on gear stress. Just a little heads up, this KQ and KQ04 will probably take a significant amount of time. So just make sure that you're starting early, start the homework early, and definitely put in a lot of effort now to get your analysis tool organized, calibrated, and make sure you practice with it.
So before we begin, I'm going to tell you where we're headed. So our goal is to understand the two types of stress that develop in a gear. So take careful notes, especially of the things that you find confusing, so we can spend time during our Zoom hours to clarify key points and work examples. So kind of take note of what you're struggling with as you go through. You should also be referencing your textbook as you complete this KQ. So use this KQ to help you focus your reading and clarify the points presented in the textbook, but you need your textbook alongside of you. And then please attempt the concept check at the end of this KQ, because there will be some quiz questions. And please don't lose heart if this all doesn't click right away. It is definitely one of the trickier 329 topics. So specifically, you should focus on understanding the different factors in the two AGMA, American Gear Manufacturing Association stress equations. And then one way to know that you understand them is if you are able to describe each of the factors that we'll cover in your own words. So here we go, AGMA stress equations. These are equations that have been developed over many decades by professionals in the field, and they're used in professional situations. They're in handbooks. They're also in Shigley, but this is the industry standard for calculating stresses in gears. The gears need to be designed to withstand both bending stress, so that would be the stress that occurs near the root of the gear tooth, and pitting resistance, so the contact stress that occurs on the surface of the tooth. And these two fundamental stress equations are used in AGMA methodology. We have one for bending stress and one for pitting resistance or contact stress. So you'll notice that some of the terms appear twice or in both equations. So the transmitted load appears in both, KO, KV, KS appears in both, face width, and KM, KM. So there are lots of different factors. I wouldn't expect you to know what any of them are, except of course for WT, that's the transmitted load. And then we know that sigma is stress. So some good advice from the textbook. Before you try to digest the meanings of all of these terms, view them as advice concerning the items the designer should consider, whether he or she follows a voluntary standard or not. So these are also just kind of designer's reference points. So you know that you need to be considering face width and overload factor and how the gear is positioned between the bearings. So add these two AGMA stress equations to your analysis tool. Do this right away, because as soon as you start programming something, your understanding of that concept just increases so much. And yes, there are a lot of K's and C's, and each of these factors will be explained on the next slides. We're going to look at US customary units only, but also note that AGMA equations are given in SI or metric units. But for your analysis tool, you only need to have the US customary or English units. All right, so let's dive into the factors. KO is the overload factor, and this is intended to make allowance for externally applied loads that may be greater than the transmitted load. So examples include, for example, an internal combustion engine. When it fires, the torque might increase from its mean value for just a short period. So you get this intermediate overload effect. These factors are usually determined in experience in a particular field. So once you've been working in an area for a long time and you've been able to make the observations. But for reference, you can use the table shown here. You can copy and paste this into your analysis tool. I adapted it from figure 1417 in the textbook. And you'll notice that we have a column for driving machine and columns for the driven machine. So an example I like to use is riding a bike. So let's say you're on a road bike. The driving machine, that's you. You're powering the bike and maybe you're pedaling pretty smoothly. So we would say you have pretty uniform, you're like a uniform driving machine. And the driven machine would be the bike. And let's say it's on a really, really flat road. So we'd say uniform. Maybe it's you're gonna go over some speed bumps, so moderate jump. Well, let's say you're a mountain biker and you're pedaling kind of erratically So you might be applying like a medium shock because you're not consistently putting power into the system. It's kind of shocky or jumpy. So maybe you're riding your mountain bike on kind of moderately rocky terrain, or maybe as in the case of this picture, this mountain biker looks like she's clearing a big jump. So we might say heavy shock. That's kind of how I like to explain it. Bike gears aren't actually gears. They're called sprockets because they don't mesh directly with each other. They mesh with a chain, but it's the same idea. Okay, so that's overload factor. Dynamic factor, when a pair of gears is driven at moderate or high speeds, you often hear a noise, and that kind of tells you that dynamic effects are present. So this factor is trying to account for these internally generated vibration loads, which are caused by like tooth contact of non-conjugate meshing of the teeth. So yeah, when you hear noise, if you were to hear noise in your car, you'd probably stop driving, hopefully, and take a look, check it out. So these vibration loads are called transmission error and are going to be worse for low accuracy gears. So how we talk about accuracy in gears is by this QV, the quality index. And this is basically just how manufacturers kind of communicate the precision of the gear. So are the gear teeth super, super well aligned? Are they a little bit imprecise? So usually we're looking at, using quality index of 8 for most commercial gearing applications. If you had, I have a grad student right now who's working on this project. It's like a crystal. He's trying to align a crystal very, very precisely, and he would have to use the most accurate gearing possible because it's a very precision application. But for our class, we're going to be talking mostly about commercial gearing applications. So quality index will be given as 7 or 8. So each of these curves vary with the pitch line velocity. So as the gears are rotating faster, you can imagine that that's kind of providing more opportunity for these unwanted dynamic effects to be present and cause some problems. So the dynamic factor KV increases, and that is going to increase the stress. So one of your quiz questions, I'll ask you something about how does KV change as a function of both pitch line velocity and gear quality, and then how does that then affect the gear stress? Size factor. So this is similar to what we learned about in fatigue. In practice, the size of a component has an effect on the stresses that develop. So we learned when we studied fatigue that larger components have a higher chance of developing a microcrack, which then can turn into a larger fatigue crack and cause fatigue failure. So KS is really just the gear tooth geometry simply incorporated with the Marin size factor in fatigue. So the Marin equation is our fundamental fatigue equation. And we're not using it exactly in that form. We're using this size factor, but it's related to the Marin equation. So in this KS formula, and I think this one, I don't think it has an equation number in the text. It's just kind of listed, but this is it. So this is how you find KS. It's a function of the face width, the diametral pitch, and then Y, which is the Lewis form factor. So this is a table in the textbook. So you can see that the factor increases as the number of teeth increases. So if you have, I don't know, let's look at this. So let's say you have a 36 tooth gear. You can just linearly interpolate between those number of teeth numbers to get the correct Y value. So it's close enough to a linear approximation. It's a curve, but we'll just linearly interpolate because you have so many data points. Nugget from Shigley, if you calculate KS to be less than 1, use KS equal to 1. Because saying KS is less than 1 would be actually saying that you have less stress induced, which would be not a conservative approach. It wouldn't actually make sense. So KS is 1. Load distribution factor, KM. So any axial misalignment or axial deviation in tooth form is going to cause the transmitted load to be unevenly distributed over the face width. So again, face width is the and then the thickness of the tooth. So this problem becomes more pronounced with larger face widths. So Km itself actually depends on 4 subfactors, and these are all 5 actually. So 1, 2, 3, 4, 5. We have these 5 subfactors. And these factors account for whether the gear teeth are crowned versus uncrowned, the gear's face width, how the gear is mounted distance-wise between the bearings, and how the gear is enclosed. So when I pull up my analysis tool, I'll show you those C factors in more detail. And I wouldn't spend too much time on dissecting each of these C factors. We could spend a lot of time here, but I'm going to give you some simplifications and assumptions to use, especially for simplification of your analysis tool. All right, rim thickness factor. Sometimes you have a gear with a thin rim, like this one. So this, the material is not extending all the way through the bore. So with thin-rimmed gears, the location of bending fatigue might be through the rim rather than at the tooth fillet. And KB is the factor that accounts for this. So to use this chart, you have to first find your backup ratio, which is MB. And, it's pretty outlined here. It's the TR over HT ratio. And yeah, so usually we're not going to be doing anything with thin-rim gears, but it's good to just have seen and to put in your analysis tool. I want to point out here that Shigley will often present both an equation and a figure or a table. For our class, it is fine just to use the figure table and not program the equation into your analysis tool unless you prefer to do that. All right, bending strength geometry factor J. So this factor J is a function of a modified value of the Lewis form factor Y. We're not going to go into it, but it's just a modified factor. The fatigue stress concentration factor KF, that was determined through lots of experimentation, and the tooth load sharing ratio MN. So again, this exists as an equation, but I think it's way better just to use this table here. So you'll notice that there's the horizontal axis. It's the number of teeth for which the geometry factor is desired. So if you were analyzing a pinion with 17 teeth, you'd start here. Let's say your 17-tooth pinion was meshing with, actually, that's not the best example. Let's say you have a 20-tooth pinion. This will be more interesting. So 20-tooth pinion meshing with a 50-tooth gear. Okay, so see how I did that? I found the 50 over here. That's the meshing gear. Pinion is what we're interested in figuring out the stress for. And then draw a line. I know that's not terribly straight, but it looks like J is about 0.32. So easy peasy. Why I didn't want to use 17 for that example is because look how everything kind of converges. So a 17-tooth pinion is going to have basically 0.3 as the bending strength geometry factor, regardless of the number of teeth of the gear. Okay. All right, so pinion and gear tooth wear. So gear analysis includes both stress and wear, and contact stress, which is the second type of stress we want to talk about, is calculated using the AGMA equation presented earlier. So here it is. This will live in your analysis tool. And note that the only new factors in this equation are CP, CF, and I, which is really nice. Other than that, it's just a rearrangement of the other factors. Note here, this always throws students off. So this DP, even if you're analyzing the gear, this is the pitch diameter of the pinion. Okay, so we use the pitch diameter of the pinion even when we're looking at the contact stress that develops in the gear that's meshing with the pinion. So just take note of that. All right, so let's start going through some of these coefficients in the contact stress equation. So elastic coefficient is a factor that takes into account the pinion and the gear materials. So again, this is one of the situations where you could insert an equation which uses Poisson's ratio and the moduli of elasticity, or just use the table. So I recommend this table. Just make sure you know how to interpret the table. So let's say we have a steel pinion meshing with a steel gear. What would be the elastic coefficient? So our pinion material, steel, gear material, steel. So this first row is corresponding to PSI. The second row is corresponding to MPa, and we're doing everything in US customary unit. So we use the first row. So 2,300, that would be your answer. Okay, so it seems like a big number, but that is what it is. Let's say you had a cast iron pinion meshing with a steel gear. So then you'd have 2,100 as your elastic coefficient. Okay, so that should be popped into your analysis tool, and that is how we use it. Surface condition factor. This factor takes into account any surface finish that might be affected by processes including cutting, shaving, lapping, grinding, shock cleaning. Some of these will induce a residual stress, and then also plastic effects, so work hardening. So these have not been established through testing. This is kind of an uncharted territory. Maybe you can do this for your PhD. So best practice is to just set CF equal to 1, unless you know that you have some detrimental surface finish, then you have to estimate your CF to be some value greater than 1. For the purpose of this class, we are going to go with CF equals 1, because again, these values haven't even been well established. Surface strength geometry factor. This is analogous to the bending strength geometry factor J in the bending stress equation, but now we're talking about contact stress. So this is also called the pitting resistance geometry factor. This is the pressure angle. The T, that's talking about, so if we had helical gears, there are multiple angles to consider because of the angle of the T. So this is referring to the transverse pressure angle, or the pressure angle on the transverse plane. For spur gears, it's just the pressure angle. So we're either going to have 25 or 20, most common 20. So 20 degrees you put in there. mg, you already know what this is. So it's the number of gear teeth over the number of pinion teeth. This is exactly what you used in equation 1311 to find the interference, the number of teeth to avoid interference. And then Mn is the load sharing ratio, and this is 1 for spur gears. So this you should just put in your analysis tool as an equation, and then pull your inputs from other places in your tool. Okay, so those are all of the factors. I know it's a lot to digest. It is going to take some time. The best way is just to practice. Again, knowing what they are kind of in your own words, and doing some practice problems. So I'm going to introduce this problem here, but this is what we're going to be studying in the virtual problem solving session for this week. So a 17-tooth, 20-degree pressure spur gear rotates at 108 or 1,800 revolutions per minute and transmits 4 horsepower to a 52-tooth gear. So we have N equals 17, N equals 52 shafts. So 1,800 RPM, and we're transferring 4 horsepower. So this is really similar to problems you've been doing, but now we're just, of course, adding on and finding the stress. So from this information, you'd be able to figure out WT. So that might be your first step. And that's something that I'll ask you on the knowledge quest quiz. So diametral pitch is 10 teeth per inches. You have the face width, and you have the quality standard. So remember, this is a little QV. The tooth profiles are uncrowned. The gears are straddle mounted with bearings immediately adjacent. So what does this mean? So if this is our shaft, here's our gear, and we're saying that the the bearings are very, very close to the gear, and this is going to come into play for one of those C factors that we talked about in the bending stress formula. Okay, the pinion is grade 1 steel, a hardness of 250 Brinell tooth, and the through hardened core. The gear is steel, through hardened, grade 1 material with a Brinell hardness of 200, tooth surface, and core. So what you'll often find is that a pinion is going to be chosen to have a higher hardness, or at least a higher case or surface hardness, because it is undergoing more rotations than the gear. So you want it to have a harder case, because we want to withstand pitting resistance, or we want to have pitting resistance. We want to withstand contact stress. Okay, the loading is smooth, so that would help us determine values for our overload factor. And the gears are in a commercially enclosed unit. Assume a pinion life of 10 to the 8th cycles and a reliability of 0.9, and use these two crazy terms. I'll talk about these in the problem solving session, but this is essentially how we account for number of cycles when we're choosing a gear or analyzing its strength. So we don't actually need these values, not needed, to calculate stress. But we will use them when we're calculating the strength.
So there's a lot going on in this concept check, lots of different parameters, things to take into account. Obviously, we're going to organize it all in our analysis tool. But before you panic, go to the next slide and see that there is actually a step-by-step process for solving these problems, which should be pretty handy. So Shigley provides a roadmap of gear bending equations based on AGMA standards. So the first thing you're going to do is something you already know how to do. So use these two expressions for pitch diameter and pitch line velocity to come up with the transmitted load based on the power. From the transmitted load, that's one of your first inputs into the gear bending equation, and then you're just going to take this one factor at a time, KO, KV, KS, etc. These will all be individual inputs in your analysis tool, which I'll show shortly. And then same thing for wear, same WT goes in here. And remember, the only new variables in this AGMA strength equation are the surface condition factor, the geometry factor for pitting resistance, and then the pitch diameter of the pinion. And remember, you have to just use the pinion here. But then what? What do we compare these stresses to? And how do we determine if these gears have enough strength and wear resistance? So a little spoiler alert, it is not as simple as comparing these values to the yield strength, for example. So remember what we did in 328 for a ductile material. We did factor of safety is the yield strength divided by the stress. In other words, the capacity of the material over the demand. And actually, the process here is no different. It's just that the processes for finding the demand and the capacity are more complicated because gears are such a wonky shape component. So in this KQ, we figured out how to calculate demand. So the demand is the bending stress and the contact stress. What we're going to do in KQ04 is calculate the capacity. So the bending strength or the bending capacity and the contact strength or the contact capacity. So through extensive testing, AGMA has come up with gear strength equations. And you're going to compare the gear stresses you calculated in the previous steps, so the demand, to these strength equations, in other words, the capacity, to determine a factor of safety. So this is the direction we'll head in KQ04. Now I will show you my analysis tool. So here is my analysis tool. I've changed the values from the concept check because I want you to do that on your own. So let's look at wear first. I have pressure angle in degrees and radians, diametral pitch, pinion diameter, elastic coefficient. So again, I'm using different values from the concept check. So your elastic coefficient, again, is this table here. So you have pinion materials and gear materials, and you find the elastic coefficient for the combination of the materials. WT is pulled from the previous sheet. Overload factor, that's coming from this table of overload factors here. Dynamic factor, KV, is this table here. And I like to use these little lines to help me read the axes. So to drop in some lines, you go insert, shape, pick your line, shape, and then draw it in. You can change the width and the color. So it's nice to be able to move these. So it looked like our pitch line velocity in this scenario was 890 feet per minute. So I would just try to eyeball that. And then the concept check, we have a quality standard number 6. So you would do your best to match, find where these two lines intersected, and then read the axis there. Size factor, Ks, is a function of the Lewis form factor and face width. So the Lewis form factor is this table here. Remember, it is based on the number of teeth that you have. If the number of teeth isn't exactly what's shown in this column or this column, you have to do linear interpolation. Km, this factor depended on 5 subfactors. So CMC is crowned versus uncrowned teeth. For our purpose, we're going to be looking mostly at uncrowned teeth. So CMC will be usually 1, but you should have this little note to yourself in case you do see a crowned tooth and a problem. CPF, this is a function of face width. Shigley gives 3 different CPF formulas based on the range of the face widths. So your simplification here is that we're going to be looking at gears that have a face width between 1 and 17 inches. The reason being that in most systems that we might see is we're not going to be working with really big gears. So this is like a pretty typical range. So you can program your CPF for this face width between 1 and 17 inches. I will not throw a curveball by giving you a smaller or larger face width than this range. CMA, this depends on 3 factors, A, B, and C, which you can get from the book, and then it also depends on the face width. Face width in inches. CF, surface condition factor, you set equal to 1 unless you have a detrimental surface finish. We talked about that, so we're just going to keep this at 1. And then the surface strength geometry factor, I, is a function of the pressure angle, and then the speed ratio. And this is the same M that you used before in equation 1311. So it's the number of gear teeth divided by the number of pinion teeth. Note that the way I have my tool set up, I need to use radians in this expression. So cosine d10 times sine d10. So I'm using radians. You should just make sure that your tool is calibrated in the right way. Using the book, checking a problem, make sure that you're getting the surface strength geometry factor that's shown in the answer that matches up to using radians versus degrees. Bending stress. So the only new factors here are KB, rim thickness factor, so you'd use this table. For the most part, we'll be doing gears that don't have a thin rim, but you never know, you might see something on the midterm or the final where you have a thin rim gear. So make sure that you have access to this table. You don't have to look it up last minute in the book or anything. And then J, bending strength geometry factor, see table. So this is again where these little lines, these movable lines are really helpful. So you line up the number of teeth for which geometry factor is desired. So that would be the gear that you're trying to calculate the stress for. And then the number of teeth of the mating gear. So I'll let you do this for the concept check. This is not the correct value for the concept check. I just threw it in there. The last thing to note, the bending stress is usually going to be lower, sometimes significantly lower than the contact stress. And this is because where contact stress is usually the dominant mode of failure for gears, but that's not always the case, and that's why we compare the wear factor of safety to the bending factor of safety to figure out what really is the dominant mode of failure, but we won't be learning about that until KQ04. So start your tool, calibrate your tool, practice with your tool. It's so important. I know I keep saying this, but I keep saying it because it's really important for the midterm. It's your success on the midterm will be in part your conceptual understanding, of course, but also how well you have your Excel tool calibrated and can use it. So I will help step you there to a calibrated tool. So we won't be solving this full concept check until videos that come later in the week, so our virtual problem solving sessions. But KQ03 is going to have some mini questions based on this concept check that are really just meant to help you calibrate your tool. So that's it. If you are a detailed Excel person, you'll probably love this part of the class. Not all of the class is so dependent on the Excel tool, but for gears and shafts, we're really going to be leveraging our tools. All right, that's it. Thanks for watching.